On a road map, symbols illustrate towns, cities, secondary roads, primary roads, airports, railroad tracks, and geographical landmarks. The same rule applies to schematic drawings. Symbols indicate conductors, resistors, capacitors, solid-state components, and other electronic parts. Every time a new component comes out, a new schematic symbol is derived for it. Often, a new type of component is a modification of one that already exists, so the new schematic symbol ends up as a modification of the symbol for the pre-existing component. Regardless of the ohmic value, all fixed-value resistors are schematically indicated by this symbol. Or sometimes this symbol. The first symbol, though, is the most universally accepted symbol for a resistor. The two horizontal lines indicate the leads or conductors that exit from both ends of the physical component. Sometimes the resistor contacts are not wire leads but more substantial metal terminals. This shows a transparent functional drawing of a carbon composition fixed resistor with leads on both ends. Here is two other types of resistors. Any resistor of the sort shown here pictorially is indicated schematically by the resistor symbol. A variable resistor has the ability to change ohmic value by means of a slide or rotary tap that can be moved along the resistive element. The variable resistor is usually set to one value, and it remains at this point until manually changed. The electronic circuit, therefore, sees the component as a fixed resistor. However, when a variable resistor is required for the proper functioning of a specific circuit, it is necessary to indicate to any person who might build it from a schematic drawing that the resistor is actually a variable type. The schematic symbol for a variable resistor with two leads looks like this. There is still only two leads. Other types of variable resistors exist, and they have three leads, two end leads and a tap. This shows two examples of schematic symbols for a three-terminal variable resistor, known as a potentiometer or a rheostat depending on the method of construction. Notice that both examples use the standard resistor configuration, and indicate that it's a variable type by means of an arrow symbol pointing to the zigzag part. Rheostats are in effect the same as potentiometers, but mechanically they differ. A rheostat contains a wire-wound resistance element, while a potentiometer is normally of the carbon composition type. Therefore, a rheostat's value varies in small increments or steps, while a potentiometer's value can be adjusted over a continuous range. In schematic drawings, an arrow often indicates variable properties of a component, but not always. Transistors, diodes, and some other solid-state devices have arrows in their schematic symbols. These arrows don't have anything to do with variable or adjustable properties. Arrows can also sometimes indicate the direction of current or signal flow in complex circuits. This is a pictorial drawing of a variable resistor of the wire-wound type, manufactured so that the resistance wire is exposed. A sliding metallic collar, which goes around the body of the resistor, can be adjusted to intercept different points along the coil of resistance wire. The collar is attached by a flexible conductor to one of the two end leads. The collar, therefore, shorts out more or less of the coil turns, depending on where it rests along the length of the coil. As the collar moves toward the opposite resistor lead, the ohmic value of the component decreases. This shows a functional drawing of a rotary potentiometer, at A, along with the schematic symbol, at B. The symbol looks like the variable resistor equivalent, but has three discrete contact points. Using the potentiometer control, the portion of the circuit that comes off the arrow lead can be varied in resistance to two circuit points, each connected to the two remaining control leads. Here we see a pictorial drawing of a typical potentiometer. Or better yet, the variable resistor shown pictorially can be changed into a rheostat by severing the connection between the collar and the end. Now, the collar can be used as the third or variable contact. Likewise, a rheostat or potentiometer can be turned into a two-lead variable resistor by shorting out the variable contact point with the lead on either end. The schematic symbol for a resistor, all by itself, tells us nothing about the ohmic value, or anything else about the component such as its power rating or physical construction. Various specifications for the component can be written alongside the resistor symbol, but these details might also appear in a separate components table and referenced by an alphabetic or numeric designation printed next to the schematic symbol, such as R1, R2, R3, and so on. You can usually determine the ohmic value of a fixed resistor by looking at the colored bands or zones on it. More on this later. Capacitors are electronic components that have the ability to block direct current, while passing alternating current. They also store electrical energy. The basic unit of capacitance is the farad, symbolized by a capital F. The farad is a huge electrical quantity, and most real-world components are therefore rated in tiny fractions of a farad, microfarads or picofarads. A microfarad, symbolized μf, equals 1/1,000,000 of a farad, and a picofarad, symbolized lowercase pf, equals 1/1,000,000 of a microfarad or 1/1,000,000,000 of a farad. This shows the common schematic symbol for a fixed capacitor. On occasion, you might see alternative symbols, such as these. Many different types of capacitors exist. Some are non-polarized devices, meaning that you can connect them in either direction and it doesn't make any difference. Others are polarized, having a positive and a negative terminal, and are marked as such. You must take care to connect them so that any DC voltage that happens to appear across them has the correct polarity. Most types of capacitors contain only 2 leads, although every now and then, you'll come across one with 3 or more leads. The basic capacitor symbol consists of a vertical line followed by a space, and then a parenthesis-like symbol, or another vertical line. Horizontal lines connect to the centers of the vertical lines or the parenthesis to indicate the component leads. The parenthesis side of a capacitor indicates the lead that should go to electrical ground, or to the circuit point more nearly connected to electrical ground. Unless the symbol includes a polarity sign, it indicates a non-polarized capacitor, which might be made from metal plates surrounding ceramic, mica, glass, paper, or other solid non-conducting material, and, in some cases, air or a vacuum. The material designation indicates the insulation, technically known as a dielectric, that separates the 2 major parts of the component. Physically, a typical fixed-value capacitor comprises 2 tiny sheets of conductive material close to each other but kept electrically separated by the dielectric layer. Notice that the symbol for a polarized or electrolytic capacitor is the same as the one for the non-polarized, but a plus sign has been added to one side. This sign indicates that the positive terminal of the component goes to the positive of the external circuitry. Occasionally, a negative symbol will also appear on the opposite side. When you see the plus sign, you know that the component is polarized, and therefore, that you must connect it to the remainder of the circuit in observance of the proper polarity. That means the positive capacitor electrode must go to the more positive DC voltage point in the circuit, and the other electrode must go to the more negative DC voltage point in the circuit. All the capacitors that we've seen so far have a fixed design. In other words, the components specified have no provision for changing the capacitance value, which is determined at the time of manufacture. Some capacitors, however, do have the ability to change value. These components are generally called variable capacitors, although some specialized types are known as trimmer capacitors or pattern capacitors. The most common symbol for a variable capacitor is an arrowed line which reveals the variable property. It runs diagonally through a fixed capacitor symbol. There is an alternative way of indicating this same component. Most of the time, the one of the first 3 will indicate a variable capacitance, regardless of the physical construction details. An air variable capacitor, one with an air dielectric, can tune many types of radio frequency equipment including antenna matching networks, transmitter output circuits, and old-fashioned radios. A typical air variable capacitor has many interlaced plates, with the plates connected together alternately to form 2 distinct contact points. The set of plates that you can rotate is called the rotor. The set of plates that remain stationary is called the stator. All variable capacitors are non-polarized components, meaning that the external DC voltage you connect to them can go either way and it doesn't make any difference. Sometimes, 2 separate variable capacitors are connected together or ganged, as in this case shown here. In a ganged arrangement, 2 or more units are used to control 2 or more electronic circuits, but both components are varied simultaneously by tying the rotors of the 2 units together. This shows the schematic symbol for 2 variable capacitors ganged together. The minimum and maximum capacitance values of the 2 components might be the same, but they don't have to be the same. They will, however, always track together. In a ganged system, when one of the capacitors increases in value, the others all increase as well. As is the case with most electronic components, the schematic symbol for the capacitor serves only to identify it and to show whether it is fixed or variable, and if fixed, whether or not it is polarized. The component value might be written alongside the schematic symbol, or the component might be given a letter and number designation. For example, C1, C2, C3, and so on, for reference to a components list or table that goes along with the diagram. A basic inductor comprises a length of wire that is coiled up in order to introduce inductance into a circuit. Inductance is the property that opposes change in existing current. It acts in practice only while current increases or decreases. Coils or inductors can range in physical size from microscopic to gigantic, depending upon the inductance value of the component, and on the amount of current that it can handle. The basic unit of inductance is
the Henry, symbolized capital H, a large electrical quantity.
Most practical inductors are rated in millihenries, symbolized by lowercase m capital H, where 1 millihenry equals 10 to the minus 3 henries, or in microhenries, Greek letter μh, where 1 microhenry equals 10 to the minus 3 millihenries, which is equal to 10 to the minus 6 henries. Occasionally, you'll see an inductor whose value is specified in nanohenries, nh, where 1 nanohenry which is equal to 10 to the minus 3 microhenries, which is equal to 10 to the minus 9 microhenries. The basic schematic symbol for an air core inductor has two leads which are designated by straight lines that merge into the coiled part. An air core coil has nothing inside the windings that can affect the inductance. Some air core coils are wound from stiff wire and support themselves mechanically, and their cores do, in fact, comprise nothing but air. In most cases, however, a non-conductive and non-inductive form made out of plastic, mica, or ceramic material serves as a support for the coil turns, keeping them in place and enhancing the physical ruggedness of the component. In some old radio receivers, you'll find air core inductors wound around small waxed cardboard cylinders resembling short lengths of drinking straws. Some hobbyists even use waxed wooden dowels to support air core coils. This shows the schematic symbol for a tapped air core inductor. In this case, the coil has two tap points along its length. Whereas the fixed coil had only two leads, a tapped coil has three or more. When a coil is tapped, separate conductors are attached to one or more of the turns for intermediate connection. Maximum inductance is obtained from connecting the end leads to the external circuitry. A tapped arrangement allows for the selection of an input or output point that offers lower inductance than the full coil does. As an alternative to taps, a coil might have a sliding contact that can be advanced along the entire length of the windings. This sliding contact allows adjustment of the inductance value, rather than having a select fixed point with the tapping arrangement. A variable coil can be indicated by either of the symbols shown here. The arrow indicates that the component can be adjusted from a maximum inductance value to a minimum inductance value. The schematic symbol for an iron core inductor looks like this. Notice that it is the basic fixed coil discussed earlier, along with two close-spaced straight lines that run for its entire length. Sometimes the iron core inductor is drawn as shown. Like this, with the straight lines inside the coil turns in the symbol. This is not the approved method of indicating an iron core inductor, but you'll still see it now and then. Some iron core inductors contain taps for sampling different inductance values. And some might even be adjustable. At higher frequencies, solid iron and laminated iron cores aren't efficient enough to function in inductors. Engineers would say that they have too much loss. At frequencies above a few kilohertz, a special core is needed if you want to increase the inductance over what you can get with non-ferromagnetic core materials, such as air, plastic, ceramic, or wood. The most common substance for this purpose consists of iron material that has been shattered into myriad tiny fragments, each of which has a layer of insulation applied to it. After the fragmentation and insulation process has been completed, the particles are compressed to form a physically solid sample called a powdered iron core. The symbols for powdered iron core inductors are nearly identical to those for solid or laminated iron core inductors, except that the straight lines are broken up instead of solid. These types of components, like all other types of inductors, can be tapped or continuously variable. A switch is a device, mechanical or electrical, that completes or breaks the path of current. Additionally, a switch can be used to allow current to pass through different circuit elements. The schematic symbol for a single-pole single-throw switch is illustrated here. This component can make or break a contact at only one point in a circuit. It's a two-position device, on or off, alternatively, make or break. A different type of switch, designated as a single-pole double-throw switch. Symbolically, the pole coincides with the point of contact at the base of the line. A throw is the contact point to which the line can point. The single-pole double-throw switch contains one pole contact and two throw positions. The input to the pole can be switched to either the upper or lower circuit point. In some circumstances, the movable part of the switch is shown with an arrow on the end of it. This is not commonplace, as you can see arrowheads, and the single-pole double-throw switch interferes with the other components of the switch, and quite frankly the arrowhead adds nothing to the logic of the symbol. Some switches contain 2 or more poles. Figure A shows the symbol for a double pole, single throw switch, while Figure B shows the symbol for a double pole, double throw switch. Some switches have even more elements. For example, by joining the ganged indicators, the switch now has 6 poles, each of which can be switched to 2 separate positions. This last designation can actually be covered under the heading of multi-contact switches. This category takes in most switches that have more than 2 poles or 2 throw positions. For example, a rotary switch has a single pole and several throw positions. The arrow still indicates the pole contact. In this case, the switch has 10 throw positions. Technically, then, it's a single pole, 10 throw, SP10T, device. Occasionally, you'll encounter sets of rotary switches ganged together. Much like 2 or more variable capacitors, rotary switches can be made to rotate in sync with one another. Here we show the schematic symbol for an arrangement that uses 2 rotary switches. The dashed line tells us that the 2 switches are ganged. The 2 arrowed lines, which indicate the throw positions, go around in sync with each other. So, for example, when the left-hand switch rests at throw number 3, the right-hand switch also rests at throw number 3. Some amateur radio operators use a special switch called a Morse code key. This old-fashioned device, also called a hand key or a straight key, makes or breaks a circuit for the purpose of sending Morse code manually. It's an SPST switch with a lever and a spring, causing the device to return to the off position when the operator lets go of the lever. This shows its schematic symbol. Throughout this discussion, a straight line has always indicated a conductor, but most circuits contain a large number of conductors. When you draw a diagram of a complicated circuit or system, you'll often find it necessary to have lines cross over each other, whether the represented wires actually make contact in the physical system or not. Here are 2 conductors that must cross each other in a diagram, but that are not connected to each other in the physical circuit, at least not at the point where they cross in the schematic. This diagram geometry does not imply that when you build the circuit, the conductors must physically cross over each other at that exact place. It simply means that in order to make the schematic drawing, you have to draw one conductor across another to reach various circuit points without introducing a whole lot of confusion and clutter, or resorting to 3 dimensions to make your drawing. A real-world circuit exists in 3-dimensional space, but when you want to diagram it, you must do it on a 2-dimensional surface. To carry off that feat, you must learn a few tricks to make sure that your readers see things right. This shows 2 ways of portraying a point where 2 wires cross and they are electrically connected at that point. In the drawing at A, one of the conductors is broken in 2 so that it appears to contact the other one at 2 different points. This geometry makes it clear that the 2 conductors, the divided vertical one and the solid horizontal one, connect to each other electrically. Black dots indicate electrical connection. In the drawing at B, the 2 conductors cross, at right angles in this example, and a single black dot is drawn at the junction. This dot tells us that the conductors connect at this point. The method shown at B might look better at first glance, but the neatness comes along with a problem. Some readers might overlook the black dot and think that the 2 conductors are not meant to connect. The method at A makes that potential misinterpretation impossible. Just as a reader might miss a black dot at a crossing point, as in Figure B, another reader might see the wires crossing in the previous slide and imagine a black dot when it isn't there. Then the reader will think the 2 wires connect when in fact they do not. This problem rarely occurs in well-engineered schematics where the draftsperson makes sure to use big black dots and good quality printing presses. However, in some older schematics you will see non-connecting, crossed wires shown like this. One of the wires has a half loop that makes it look like it jumps over the other wire to avoid contact. That trick, which should never have gone out of style, in my opinion, gets rid of any doubt as to whether the wires electrically connect at the crossover point or not. A cable consists of 2 or more conductors inside a single insulating jacket. In many cases, unshielded cables are not specifically indicated in a schematic drawing, but appear as 2 or more lines that run parallel to indicate multiple conductors. Shielded cables require additional symbology along with the conductors. This figure shows examples of shielded wire ungrounded at A and grounded shield at B, often used to indicate the use of coaxial cable in an electronic circuit. Coaxial cable contains a single wire called the center conductor surrounded by a cylindrical, conduit-like conductive shield. An insulating layer, called the dielectric, keeps the 2 conductive elements isolated from each other. In most coaxial cables, the dielectric material consists of solid or foamed polyethylene. At B, as well as this figure shows a symbol for coaxial cable when the shield connects to a chassis ground, such as the metal plate on which an electronic circuit is constructed. The chassis ground might lead to an earth ground, but that's not always the case. In a truck, for example, no earth ground exists, so the chassis of the trucker's CB radio would go to the vehicle frame. In some cables, a single shield surrounds two or more conductors. This shows the schematic symbol for a two-conductor shielded cable. This symbol is identical to the one for coaxial cable, except that an extra inner conductor exists. If more than two inner conductors exist, then the number of straight, parallel lines going through the elliptical part of the symbol should equal the number of conductors. For example, if the cable contained 5 or more conductors, then 5 or more horizontal lines would run through the elliptical part of the symbol. This shows the basic symbol for a semiconductor diode. In this symbol, an arrow and a vertical line indicate parts of the diode, and the horizontal lines to the left and right indicate the leads. The symbol portrays a rectifier diode. The arrowed part of the symbol corresponds to the diode's anode, and the short, straight line at the arrow's tip corresponds to the cathode. Under normal operating conditions, a rectifier diode conducts when the electrons move against the arrow. That is, when the anode has a positive voltage, with respect to the cathode, standard current will flow in the direction of the arrow. When the anode has a negative voltage with respect to the cathode, standard current will be blocked. Here are the symbols for some specialized diode types. At A, we see a varactor diode, which can act as a variable capacitor when we apply an adjustable DC voltage to it. At B, we see a Zener diode, which can serve as a voltage regulator in a power supply. At C, we see a gun diode, which can act as an oscillator or amplifier at microwave radio frequencies. A silicon-controlled rectifier, SCR, is in effect a semiconductor diode with an extra element and corresponding terminal. Its schematic symbol appears here. In the SCR representation, a circle often, but not always, surrounds the diode symbol, and the control element, called the gate, shows up as a diagonal line that runs outward from the tip of the arrow. In all cases, the lead that goes to the base of the arrow is the anode of the device, and the one connected to the short straight line at the arrow's tip is the cathode. This slide shows the schematic symbols for bipolar transistors. The PNP type, followed by the NPN variety. The only distinction between the two is the direction of the arrow. In the PNP device, the arrow points into the straight line for the base electrode. In the NPN device, the arrow points outward from the base. Occasionally, the circle that surrounds the base, emitter, and collector leads is omitted from the bipolar transistor symbol. Besides the bipolar variety, many other types of transistors exist. This slide shows the symbols for another 4 devices, as follows. At A, we see an N-channel junction, field effect transistor. At B, we see a P-channel junction, field effect transistor. At C, we see an N-channel metal oxide semiconductor, field effect transistor. And at D, we see a P-channel metal oxide semiconductor, field effect transistor. Transistors can be made from various types of semiconductor materials and metal oxide compounds, but the schematic symbol, all by itself, tells us nothing about the elemental semiconductor material used in manufacture. The symbol merely indicates the component functionality. The junction field effect transistor is often referred to as a JFET, and the metal oxide semiconductor field effect transistor is often referred to as a MOSFET. Although vacuum tubes aren't used in electronics nearly as often as they were a few decades ago, many designs still exist that do employ them. When you want to create the symbol for a vacuum tube, you should start by drawing a fairly large circle. And then you would add the necessary symbols inside the circle to symbolize the type of tube involved. The schematic symbols for the various types of tube elements commonly used in schematic drawings are shown on this slide. Filament or directly heated cathode. Indirectly heated cathode. Cold cathode. Photocathode. Grid. Anode or plate. Deflection plate. Beam-forming plates. Envelope for vacuum tube. Envelope for gas-filled tube. All tube elements are surrounded by a circle, which represents the tube envelope. Occasionally, the circle is omitted from some tube symbols in schematic drawings, but that's not standard practice. This slide shows the schematic symbol for a diode vacuum tube. This 2-element device contains an anode, also called a plate, and a cathode. Just as with the semiconductor diode, the anode is normally positive with respect to the cathode when the device conducts current. The cathode emits electrons that travel through the vacuum to the anode, but blocks electrons from flowing to the cathode from the anode. This means that standard current flow will flow from the anode to the cathode, but blocks current flow from the cathode to the anode. A hot wire filament, something like a miniature low wattage light bulb, heats the cathode to help drive electrons from it. The filament has been omitted for simplicity, a common practice in all vacuum tube symbology when the filament and cathode are physically separate, an arrangement known as an indirectly heated cathode. This shows two versions of a triode vacuum tube, which consists of the same elements as the diode previously discussed, with the addition of a dashed line to indicate the grid. The tube at the left has a directly heated cathode, in which the filament and the cathode are the very same physical object. We apply the negative cathode voltage directly to the filament wire, no separate cathode exists. In the tube at the right, we see the symbol for a triode tube with an indirectly heated cathode. In this symbol, the filament is inside the cathode. Tetrode vacuum tubes have two grids. To represent one of them, we need an additional dashed line, as shown in these drawings. In the tetrode, the upper grid, closer to the anode, is called the screen. This shows symbols for the so-called pentode tube, which has 3 grids and a total of 5 elements. In the pentode, the second grid, going from the bottom up, is the screen. And the third grid, just underneath the plate, is called the suppressor. Again, the left-hand symbol portrays a device with a directly heated cathode, while the right-hand drawing shows a device with an indirectly heated cathode. In all the vacuum tube symbols shown, electrons normally flow from the bottom up. They come off the cathode, travel through the grid or grids, if any, and end up at the plate. Once in a while you'll see a vacuum tube symbol lying on its side. In that sort of situation, you can simply remember that the electrons go from the cathode to the plate under normal operating conditions. Some vacuum tubes consist of 2 separate, independent sets of electrodes housed in a single envelope. These components are called dual tubes. If the 2 sets of electrodes are identical, the entire component is called a dual diode, dual triode, dual tetrode, or dual pentode. This shows the schematic symbol for a dual triode vacuum tube with indirectly heated cathodes. In some older radio and television receivers, tubes with 4 or 5 grids were sometimes used. These tubes had 6 and 7 elements, respectively, and were called hexodes and heptodes. These esoteric devices were used mainly for mixing, a process in which 2 RF signals having different frequencies are combined to get new signals at the sum and difference frequencies. The schematic symbol for a hexode is shown on the left, the symbol for a heptode is shown on the right. Some engineers called the heptode tube a pentagrid converter. Both of these symbols show devices with indirectly heated cathodes. You won't encounter hexodes and heptodes in modern electronics, but if you like to work with antique radios, you should get familiar with them. But take this warning, you'll probably have a difficult time finding a replacement component, should one of these relics go soft on you. A cell or battery is often used as a power source for electronic circuits. This is the schematic symbol for a single electrochemical cell, such as the sort that you'll find in a flashlight. A single cell component such as this usually has an output of approximately 1.5 volts DC. Electrochemical batteries with higher voltage outputs comprise multiple cells connected in series, negative to positive in a chain or string, such as this. The multi-cell battery symbol is simply a number of single-cell symbols placed end-to-end without any intervening lines. If a circuit calls for the use of 3 individual, discrete single-cell batteries in a series connection, you might draw 3 cell symbols in series with wire conductor symbols between them. Alternatively, if multiple individual cells are set in a battery holder designed for direct series connection, you can use a battery symbol to portray the whole bunch. Standard practice calls for polarity signs to go with the symbols for cells or batteries. Unfortunately, some draftspeople neglect this detail. When you see the schematic, you'll have to infer the polarity by scrutinizing the rest of the circuit, although it is customary for the longest line to be the positive end. You'll encounter lots of symbols in electronics other than the common ones shown in this chapter. There are many more schematic symbols in addition to the ones already discussed. There are also symbols for jacks and plugs, piezoelectric crystals, lamps, microphones, meters, antennas, and many other electronic components. It might, at first thought, seem like a massive chore to memorize all of these symbols, but their usage and correct identification will come to you with practice and with time. The best way to begin the learning process is to read simple schematics and refer to listing of symbols whenever a symbol crops up that you can't identify. Within a few hours you'll be able to move on to more complex schematics, again looking up the unknown symbols. After a few weekends of practice, you should be thoroughly familiar with most electronic symbols used in schematic representations, so that when you see one in a diagram, you'll recognize it without having to think about it. Schematic symbols are the fundamental elements of a communication scheme, like the symbols in mathematical expressions or architectural blueprints. Most schematic symbols in electronics are based on the structure of the components or devices they represent. Schematic symbols often appear in groups, each of which bears some relationship to the others. For example, you'll encounter many different types of transistors, but they're all represented in a similar fashion. Minor symbol changes portray variations in internal structure, but all can be easily identified as some type of transistor. The same rule applies to the symbols for diodes, resistors, capacitors, inductors, transformers, meters, lamps, and most other electronic components. This information, as well as other related electrical blogs, may be found on my website at https://www.getpspt.com. There you also have access to my courses, which are continuously being added to, and at the present time include the following. This is the end of this chapter.